Hello everyone, my name is Felicia, and today I'm going to explain to you about this game called Mastermind and how we are going to solve it using the brute force and decrease and conquer algorithm and compare both algorithms. First of all, I'm going to explain to you about the rules of the games. As many of you may be familiar with this game, we have here a decoding board and 6 different colored packs. The aim of this game is to be able to uncover the hidden code that has been set by the computer. We will have to pick guesses, and then the computer will give us feedbacks on which colors we put are the correct color but at wrong position, and which ones are the correct color but at the correct position. So here, let's take a pick. Let's see, we pick all yellows. The computer gives us no feedbacks, so it means that there are no yellows in the hidden code here. Next, we'll try the oranges. Here we get one black pack, which means that there's one correct color at the correct position, so there's one orange in this code. Next, we'll try to combine it with reds. Oh, we see that there are 2 reds, and this orange is at the wrong position. Why do we know this? Because it is impossible if the reds are at the wrong position. So we'll just take the orange and reds and make a new combinations. Try each one of them. Here we see that blue is not included. And then we'll try red, orange, not that dark red. Alright, still incorrect. So about green, red, and orange. Here we have the solution, which is correct. We have guessed this in only 6 guesses. So after we have seen the demo, it should be clear enough about the game. So we'll move on to the algorithms, which are brute force and decrease and conquer. The first algorithm we'll discuss is the brute force algorithm. In computer science, the brute force algorithm is a general algorithm which can be utilized to solve almost all computational problems. This algorithm consists of systematically enumerating all solution candidates and checking whether each candidate satisfies the problem statement. Brute force algorithms are usually based on the problem statement itself or definitions and concepts regarding the problem. So it means in a game of Mastermind, a brute force approach is to just enumerate all possibilities. Actually, there are 1296 possibilities of this solution code and try it one by one to see if one of them matches, which is actually pretty impossible. And also, we are only given a chance of 6, 7, 8 or 9 guesses here, so it's not possible. So to reduce the number of guesses needed to uncover the hidden code, we'll have to use a heuristic. This time I'll use the heuristic, which is the first 6 guesses of the algorithm are dedicated to discovering the colors and the frequency of each color making up the solution code. So we'll have to know how many yellows are in this code, how many oranges, how many reds, blues, darker reds, and greens. How do we do this? We do this by guessing single colored guesses like this one, this first 2, like yellow, 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 orange, 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 and then by looking at the black packs, the amount of black packs that is in the feedback, we'll know how many colors, how many of that color is in the hidden code. So let's see this in action. Oh, my bad. We'll have to go to the brute force folder first, and then we run the Python code. here we see that the computer has picked a solution code of 4665. These numbers are only substitutes for the different colors. Let's just say that 1 equals to yellow, 2 equals to orange, and so on. So here we have 4665, the solution code, which actually should not be revealed at first, but in order to be able to understand this more, we'll have it revealed. The first attempt is to guess 1111, and then we see that there are 0 black packs and 0 white packs, which means that there is no 1 in the solution code. The algorithm then continues to attempt 2, 2, 2, 2, 3, 3, 3, 3, and so on. Here in the 4, 4, 4, 4, it gets a feedback of 1 black pack, which means that there's only 1 4 in here. And then in the 5, we get a 1. And then in the 6, we get 2 6s. So we have this all of the components that we know. And then after that, the second half of the algorithm is the brute force algorithm, which is enumerating all permutations of the components that we have found. So we'll try 6, 4, 5, 6, and so on, all of the combinations tried to see which one matches. Here at the 11th attempt, we get a match. So that is how the brute force is done. From this, we can see that the worst case scenario is only 30 guesses instead of 1296 guesses, which is a way reasonable amount, I suppose. Where do we get this 30 from? So we get this from this one, 6 guesses into first, and then after that we'll have 24 permutations, because 4 factorial is 24. So a total of 30 guesses. It is also worth noting that this algorithm performs better with codes that have more repetitions of colors, since the generated possible permutations contain more duplicates which could be eliminated. And then we will see about the statistics. Here I run a program that runs the brute force code for all 1296 possibilities of the solution codes. It takes 15 guesses to guess the solution code or the answer code 1135 and 11 and so on. So this is the statistics. The total time needed to solve all possible solutions is 0.8711 seconds, which means it's under 1 second, which is pretty fast. And then the average guesses, however, is 12.8025, which means that this algorithm is not really viable for a real Mastermind game, since the real Mastermind game has a limit of guesses which you could guess, and also the worst case scenario is a whopping 30. So we move on to the next algorithm, a better one, of course. Now we see that we can also use the decrease and conquer algorithm to solve this. How do we do this? The decrease and conquer algorithm starts with a set S of all 1296 possible combinations, and then over time, with each iterations or with each guess the algorithm makes, it will eliminate all the possible combinations from S which are not consistent with the feedback received, meaning that we have in this S only the possible solutions. So let's see this code in action. Here we see that it takes only 5 guesses to guess the code 5643, which is way better than our first algorithm. This first attempt is just a random number that the algorithm guesses. It's 4652, and then it receives a feedback of 1 black packs and 2 white packs. And then from this feedback, it will eliminate all solutions, all candidate solutions, from the list of 1296 possible combinations, so that we only have the possible solutions only. For example, we will eliminate from our list 4444, because if the answer is actually 4444, then it wouldn't have these two white pegs as the feedbacks, and so on until we only have a limited amount of guesses. And here we have broken the code. Like before, we can also see the statistics. We see that this program is way slower than the first program. Why? Because in this program, the algorithm needs to think first before it guesses. So in the brute force algorithm, it just fires whatever guess it can. But here, we'll have to eliminate all the possible solutions that are impossible. So the algorithm will only guess the possible solutions. Here it takes quite a long time. Let us wait while this runs. It's already on the 3. Two and 1. Alright, almost done. Here we see that the total time to solve all possible solutions is 68.9139 seconds, which is way over a minute. Very different from our first brute force algorithm. But our average guesses is only 4.6373. It means that the algorithm can guess the code in about 5 moves only. And the worst case scenario here is only 7, but it is worth noting that this number is actually quite random due to the randomness of this algorithm. The actual worst case scenario is actually 8. So when compared to the brute force algorithm about the time, we can see that the decrease and conquer algorithm takes more time, which I've already explained before, but the guesses are lower. But there are also other factors. The computer and the human mind are two different things. For a beginner human player, the simplicity of the brute force algorithm makes it easier to understand and implement in a game of Mastermind. The player simply needs to follow a methodical approach without plenty of thinking to be able to determine the code. On the other hand, the decrease and conquer algorithm requires a deeper understanding of the game and careful deliberation each time the player needs to make a guess. Therefore, a beginner player may find it easier to initially practice code breaking with a brute force algorithm before moving on to a more advanced decrease and conquer algorithm. So, in conclusion, the brute force and decrease and conquer algorithm are both viable strategies to implement in a game of Mastermind, but both with their own trade-offs. The brute force algorithm is well suited for games without a maximum number of rounds and when one has reasons to believe that the solution code contains repetitions of colors. On the other hand, the decrease and conquer algorithm guarantees a win in less than 8 rounds, which means that it is suitable for more complex games with a rule of a certain maximum number of rounds and also for more advanced players. So those are the conclusions of these experiments. Thank you for listening.